So welcome to the Nptel MOOC on the design and analysis of algorithms. So here are some of the things that we will be looking at in this course. When we study algorithms, the first thing that we need to convince ourselves is that the algorithm is correct, that it's doing the job that we expect it to do. So we will look at strategies for proving the correctness of algorithms. The other important aspect of algorithms, of course, is efficiency. How much time does the algorithm take on inputs? Now, of course, we have to factor in the size of the input, and we need a notation or a way of comparing two different algorithms which operate on the same types of inputs and produce the same types of outputs. So this will be achieved through the concept called asymptotic complexity, which measures the running time of an algorithm as inputs grow larger and larger as a function of the inputs. And we will develop some notation, typically the big O notation, in order to smoothen out some idiosyncrasies of algorithms and group them into large chunks which are equivalent. An important part of problem solving in any domain, and in particular in algorithms, is the art of modeling the problem at a suitable level of detail. In most algorithms that we will see, we need to find a suitable mathematical model. One of these will be graphs. We need a way of representing the concepts of these models in our algorithm. For this, we need appropriate data structures. And of course, typically, in order to solve a problem, we need to break it down into manageable subproblems. So we will look at strategies to decompose problems into smaller problems and see how to put them together to solve the problem at hand. Over the course of time, many generic techniques have been developed to solve a large number of problems. And we will see examples of how these techniques can be applied to very standard problems that we come across repeatedly. Among the techniques are divide and conquer, where we break up the problem into individual components which do not overlap with each other, and then combine these solutions in order to get the solution for the overall problem. In some cases, we can identify a strategy which looks at the local state of the problem and chooses an optimal path and arrives at the final solution without having to look at all possibilities. These kind of greedy algorithms are rare. It's important to know how to prove such an algorithm is correct. But if a greedy algorithm does exist, it is typically much more efficient than other types of algorithms. When greedy doesn't work, we need a systematic way of exploring all the possibilities and choosing the best one. In this process, sometimes we have to discard overlapping problems and make sure that we don't wastefully recompute things. So this is covered by the concept of dynamic programming. Now, along with the theory in this course, we will have some programming assignments. So we do expect that all of you have some background in programming. Now this could be in C or C++ or Java. We are flexible about the language we use, but you should be able to write standard programs and implement some of the basic algorithms that we are using in our course. In order to do this, we will of course cover some new data structures in this course, but we do expect that in the language that you use, you are familiar with basic concepts like arrays and lists, and also things like stacks and queues which build upon these. Of course, when we come to stacks and queues, we will try to give some detail about how they are used. But we do expect that you have seen them before, so this is not the first time you're seeing these concepts. Here is a kind of approximate list of the topics we expect to cover in the course. So after looking at a few examples, we will start with asymptotic complexity, which is the way of measuring the efficiency of an algorithm and writing down this measure in a way that we can compare easily across algorithms. We will then move to the most basic problem that we have for arrays, which is to search an array for an element. And in the process, we will realize that it's important to be able to sort the array efficiently in order to arrange the elements in a way where we can search in an effective manner. So we will look at searching and sorting. So we will look at binary search, and we will look at different notions of sorting, some of which are more elementary and intuitive, like insertion sort and selection sort, but are not the best in terms of efficiency. And then we will look at more efficient algorithms like merge sort and quick sort, which are not obvious to begin with. Moving on from searching and sorting, we come to graphs and graph algorithms. So we will introduce graphs, We will see how we can use them to model certain types of problems. We need to know how to represent a graph. A graph is essentially a picture. So how do you translate this picture into something that an algorithm can manipulate? So that's representation. We will look at standard problems in graphs, reachability and connectedness. We will look at a special class of graphs called directed acyclic graphs, which are very useful for modeling certain kinds of problems. And then we will look at other canonical problems on graphs, including shortest paths and spanning trees. As we mentioned before, there are some basic algorithmic design techniques which apply across a class of problems. So we will look in particular at divide and conquer, greedy algorithms, and dynamic programming. Among the data structures that we will encounter in this course are priority queues, which are often implemented through heaps. We will look at binary search trees, which are efficient ways of maintaining information in a sorted order dynamically as information comes and goes. And we will look at a very useful data structure to maintain a partition of a set into a disjoint collection of subsets, the so-called union find algorithm. And finally, depending on how much time is left, we will look at some miscellaneous topics. It's important to realize that not every algorithm admits an efficient solution. So we will look at problems of intractability and some provably hard problems and some other problems for which the status is unknown. This is an 8-week course. The tentative schedule is as follows. In the first week, we will do some motivating examples and we will look at some notations and work out some problems involving asymptotic complexity. In the second week, we will move on to searching and sorting. In the third week, we will introduce graphs and look at basic graph algorithms. We will continue with more graph algorithms and then in the process introduce the disjoint set data structure. We will then formally look at divide and conquer, which we will already have seen along the way, but we will look at it again. And then we will introduce heaps. In the 6th week, we will do search trees and some examples of greedy algorithms and their proofs. The 7th week will be devoted to dynamic programming. And in the last week, we will cover miscellaneous topics. Now you should remember that this is only an approximate schedule and there will be some variations, but roughly this is the sequence and the speed at which we plan to cover the material in the course. You can also see alongside the weeks, the calendar weeks that these correspond to. So the first week of the course is the current week, which is January 5th to 9th, and this course will go on to the last week of February. Now, as part of the evaluation for the course, there will be continuous evaluation. Every week there will be quizzes. There will also be programming assignments, roughly 6 programming assignments across the 8 weeks. After the course ends, there will be a certification exam. In order to get a certificate that you have successfully completed this course, you need to score 60% in the quizzes and in the certification exam. You need to submit at least 5 or 6 out of the 6 assignments, and at least 4 of them you must do something non-trivial. We will be following 2 main textbooks, although I will not use the textbooks directly in the course, but if you want to look up some material, you will find them in these 2 books. The first book is called Algorithm Design by John Kleinberg and Eva Tardosh. And the second book is just called Algorithms by Sanjoy Dasgupta, Christos Papadimitrou, and Umesh Vaisirani. The book by Kleinberg and Tardosh is more detailed, and it has a number of really nice examples to illustrate many of the concepts and quite detailed proofs. The book by Dasgupta, Papadimitrou, and Vaisirani is a slimmer book. It's more easy and accessible to read on your own. But on the other hand, it does leave a lot of details as exercises. So in order to really understand the material, you really need to spend more time working out the exercises and not just go by the material that's presented in the chapters.